I mean, it's, you know, it's at the bottom of the earth and it's so far away from everyone, and why do we even care about it? Hopefully you'll get from this talk, by the end of it, you'll realize why it's so important to us all. This here is going back to 1840. If any of you are familiar with Hobart, Australia, this is around the time of when they built the Kelly Street steps that would go down to Salamanca Place. And on the right is a little newspaper clipping from the Hobart Gazette. And this was when the Antarctic continent was first reported to have been discovered. And what is so delightful here is what's highlighted in the top three lines. An interesting rather than important geographical discovery has this year been made in the southern Antarctic Ocean. I mean, they really could not have been more wrong with that sort of what they decided about the fact it wasn't important, because it really is very important. And I'm going to explain to you why. This is another quote that comes from an Australian explorer, Sir Douglas Mawson. I love this quote. It was actually at the front of my PhD thesis. I still use it in various places, but and actually, as we landed on the beach that I'm going to show you at the end of this talk in February this year, the expedition lead recited these words to us from Sir Douglas Mawson. So it has a lot of significance to me. So we came to probe the Antarctic's mystery, to reduce this land in terms of science, but there's always the indefinable, which holds aloof, yet which rivets our souls. It's an incredible place. It's full of mystery. We really still don't understand it, but we do know that it's very important to us all. So I'm just going to, on the right here, show you what an ice sheet looks like if you just make a schematic, and this is a cutaway, thinking about the time scales on which ice shelves change compared to other things in the cryosphere. And ice sheets are changing on these long time scales. They're kind of like every thousands of years or so, or every century or so, they might change. They're very, very slow moving though. And this is what we have been thinking. This is the IPCC fourth assessment report, which came out in 2007. We still thought this at that time. And so what I'm going to try hopefully convey to you today is that actually it's not as simple as that. It's not just a slow moving, like glacial pace is actually no longer incredibly slow moving all the time. There is actually this small or short time scale changes that occur around the edges of the ice sheets that are very important to us because they are actually affecting the behavior of the whole thing. And so we're going to get into that. So no longer do we have these like long time scales where Antarctica doesn't matter because it's not going to change. That's no longer true. So here's 100 years of human history and exploration in Antarctica. We're all familiar with, you know, Shackleton, and this is actually after the First World War, the British Antarctic Survey setting up camp. This here is the first all-female science expedition to the South Pole, the year I was born. And very significant actually when women were finally allowed to go to Antarctica and undertake science. This here is me on the Amory Ice Shelf in the mid-90s during my PhD. And here is my former student, Matt Siegfried, who's now an assistant professor, and my current student, Philip Arndt at Scripps, and they are just landing on the ice at McMurdo. So this is kind of my story twisted into this, but also like showing, you know, what 100 years looks like and the time scale of Antarctica. This is what Antarctica looked like in terms of mapping, because obviously the most important thing or the most basic thing we need to know about Antarctica is, you know, where is it? What shape is it? How much ice is there? These are kind of questions that you would sort of think that we had the answers to. Well, it turns out it's not so easy because it is so far away across that treacherous Southern Ocean, very difficult to get to, and turned out very challenging, even in the early 1900s, for ships to get there and make observations, to the point that the whole west side of Antarctica was just not mapped at all. I mean, it's just this like mass of white and blue nothingness with no edges. And so this is completely wrong, actually. They did get the east side of Antarctica fairly well mapped, and that's because a lot of the ships were able to get there from Hobart. So that newspaper clipping I just showed you, so other ships were able to go and take a few more measurements. So we got pretty good handle on what this side looked like. This was a big mystery over here. The Antarctic Peninsula is more accessible, obviously, from South America, and so go across the Drake Passage. And there was definitely some good mapping going on there. But there was this whole area that was just not known about as recently as 90 years ago, which is quite staggering. Okay, so there was a lot of ramping up of activity. As I said before, like after the Second World War, there was this Operation High Jump, which was a military, US military led expedition, and there was a lot of naming of features and mapping and planes and all sorts of things going there to make measurements and try and get an idea of the shape and the structure of the ice and how much is there and get a bit more of the mapping done. So they went around the west of Antarctica and the east of Antarctica and named everything, and was able to successfully sort of come back and report back some of that to the science community. There was another newspaper article in Hobart about this, the mapping of Antarctica and how they did it with the seaplanes, and the US military basically taking everything they could to try and understand this mysterious continent. And then there was a big sort of ramping up of activity in the International Geophysical Year in the 50s. And this is when a lot of geophysical observations began. Some of the time series that we still have going today were started in 1957. And so the Antarctic Treaty was also signed during this time. And, you know, this was really a new era of understanding Antarctica. I have here the Keeling curve, and this is actually a photograph of the plaque on the wall at the Scripps building. And this is showing, this is another observation that we've been making since the International Geophysical Year. This is obviously the carbon dioxide in the atmosphere at Mauna Loa, Hawaii. And so, you know, this was a time where scientists all around the world were starting to observe many different things, and Antarctica was no exception. And we got a lot of data. An important time series began at that time in Antarctica. So moving on now to the new era in understanding Antarctica. And this is, so previously, all of this is mainly sort of on the ground and a little bit airborne. This is where we're sort of up to here. But the big change, a very big step change in our understanding of Antarctica came in the 70s. And that is because we launched some satellites. And so Earth observation from space has been an incredibly transformational contribution to understanding Antarctica. And that is because of the fact that it's such a vast continent, so far away, so hard to get to, even with planes. I mean, very, very difficult to map something that's so large and so far away. And the only way that you can really do that is by launching a satellite and having it observed remotely from space. And so these are the two sort of first images that came from Landsat. This is on the left, the Lambert Glacier in East Antarctica, and then on the right, the Pine Island Glacier in West Antarctica, which we know now is changing very fast. It might have been at this time, but we didn't really have time series to compare it to, but we know now that it is. And so this was really a big change. We're able to now to image from space and compare just time series of satellite images and see how the ice is changing, which was a huge change in our capability. So this is my sort of story merged in here. I mean, around about this time, I was, brought into the world, and I was lucky enough to go to school in Manchester. I'm from the UK, and I met an amazing teacher. Actually, I gave this exact talk about a month ago, and Melissa Lord was actually had asked me to give a talk like this, and so this feature on her is sort of for that, but I left it in here because I think it's nice to kind of see the story. And this was me, like a disinterested teenager, didn't really care about anything apart from Duran Duran. But I met this wonderful teacher, and she got me interested in physics, and she was phenomenal. And we're still in touch, which is really nice. And so I ultimately ended up going to MSSL, which is the Millard Space Science Laboratory, part of UCL, University College London. And I was very fortunate there because I was able to take a class with Chris Rackley, who I think Nigella knows Chris, and he's a wonderful person, and he actually introduced me to Seymour Laxton, and we were able to do this project, which was tracking icebergs that had calved from Antarctica in successive images. And this was like a whole new thing at this time. I mean, this is in the 80s and 90s. Actually, it was the 90s. I wasn't at college in the 80s. So this was like a really, really transformational, again, sort of application. We're able to now not only map things, but also map how they're changing with time, and looking at iceberg trajectories tells you about currents and things like this. So this is, like I said, in the 90s. And at this time, the first IPCC report came out. And this was quite important in terms of this story I'm trying to tell, because this report here on the right was basically said the ice sheets aren't really changing. We don't really care about them. They're not that important for climate. On human timescales, we don't need to worry, right? So this is kind of like, I go off to do my PhD, and this is what people are thinking about Antarctica. It's not really changing that much. Well, I mean, they couldn't really have been more wrong. And I'm about to show you some of the changes that have taken place. But before we get there, I'll show you a mosaic that came out around about that time as well. And this is now stitching together multiple images of satellite data over the whole continent. So now the whole of Antarctica is laid out in front of your eyes, and people were able to see like things that they never had seen before jump out at them, all because of this amazing technology from space and being able to like just look at everything underneath all at once and see like ice streams and how they flow and onto the ice shelves, which are these parts here. And I'll talk to you about why they're so important in a minute. And this was very big. Bob Binshadler, who's now retired, he told me that this was his aha moment in glaciology when he saw this laid out like this. It was finally, wow, we've been looking at little bits of the continent, and we never really understood how the whole thing worked together. But this map changed their whole view. So we'll jump forward to me doing my PhD and why I was on the Amory ice shelf, why I was standing there with this pole. What's that all about? Well, actually, there's an interesting story behind that pole. So this is, I was very interested in moving to Australia at this time. I'd grown up in the UK and spent a gap year in Australia and didn't really want to live in the UK anymore. So went to Australia to do Antarctic work. And if you are working in Antarctica in Australia, you end up in Hobart because that's close, as I said at the very beginning. And so I was very lucky there. I went to the University of Tasmania. Richard Coleman, Ian Allison, and Neil Young were my PhD supervisors. And here on this particular survey here was very early days of GPS. This is in the mid-90s. GPS had really only been around for a very short time. And so we were doing a survey of the ice shelf to understand the surface, how high it is, to calibrate satellites that are actually measuring the height, altimetry, because the first altimeter had just been launched. This pole was put in the year before I was born. Right here, you can see, maybe it's not the exact poll, but it was a survey that had been put out in the late 60s on the ice shelf by these surveyors. And so this was pretty amazing to actually find these same polls, and some of them have been buried even deeper than this. But this one was standing, a little bit taller than me, and you can see when they went in, they were really, really tall. So they've been buried by accumulation. So that gives us some idea about accumulation rates on the ice shelf. This is a survey that we did. We went around GPS on these grids, 10 kilometers grid, 10 kilometer squares. This is a lot of driving, 22 days on the ice shelf, camping, moving the camp. It was a lot, but it was definitely a very good way to see the continent. We also did similar surveys like this actually on places that are not Antarctica, because if you're calibrating an altimeter, you just need a flat surface. And so we've done this on the Saladia Uni in Bolivia, and also the Simpson Desert in Australia, which is right here. So this is what it looks like when you get an altimeter satellite and you've calibrated it and you make a map of the whole ice sheet. And this was around about the same time that I was doing this survey in the early 90s. This is a map of surface elevation now. It's the height of the ice sheet. So not just looking at it with a photograph, but actually what is the relief? What's the 3D shape and structure of the ice sheet? And the altimeter was able to tell us that. So that's what this is a hole. You'll see there's a hole here, a discontinuity. That's because near polar orbits can't go all the way to the South Pole. So there is always a gap. So this gap turned out to be quite large. But you can see some real features here that are very, really important for understanding the glaciology of the ice sheet. So these ridges here, the subglacial lake, things like that. Very useful information for modeling and understanding the ice sheet and how it works. You can also look at just the ice shelves. So these ice shelves around the edges of Antarctica, and they're playing a very vital role. And I'll tell you about that in the next slide. But first of all, just want to show you the thickness of these ice shelves. So this is sorry, it's a rainbow color scale. We're not supposed to use those anymore, but this is, you can see around 100 meters thick, so about 1 kilometer thick around the very edges of some of these ice shelves. And then Amory ice shelf actually goes all the way to 2.5 kilometers deep. And so these are very substantial blocks of ice that are actually holding back the ice behind it. But there's also some interesting things going on underneath the ice, in the ice shelves, in the cavity, to do with the interaction with the ocean that we were able to go and sample once we had a map of how much ice there was underneath there. And we were able to do that because of the combination of the altimetry with some airborne data as well. So this is a field campaign that started because of the work I did during my PhD, mapping this under ice accretion. So ice shelves, again, I've said they're really important. This is why they're important. They hold back the ice behind them. So the grounded ice is what we're worried about. If you think about a glass of water, if you have ice cubes sitting in a glass of water, if the ice melts, the level doesn't go up. So that's like what happens when you melt an ice shelf. The level doesn't go up of sea level. But if you add more ice cubes into your glass, then the level of the water will go up. And that's the grounded ice behind the ice shelf. So the ice shelf is kind of like holding back, like a buttress. I have an analogy here. These architectural buttresses that you see on cathedrals in Europe and the UK, you could, well, here too, probably. I just know this one is actually Bath. So you actually, just like that, the ice shelves are buttressing, holding back the grounded ice, and the grounded ice is the sea level contributor. So it's a bit like these dams that we see. And, this is our ice shelf is basically downstream of the dam, and the grounded ice is upstream of the dam. And you don't want the dam to break. The dam is holding it all back. And once the ice shelves weaken, you weaken the buttress, you weaken that ability of the ice shelf to hold back the grounded ice, and more ice is going to ultimately end up leaving the continent. And the only place it can go is the ocean. And the ocean is seeing this. We are seeing sea level rise that's increasing because of more and more ice slowly finding its way off the continent and into the ocean. And it's happening faster and faster. And this is something that we're very concerned about, especially in East Antarctica. And then this is, this is just explaining the mass balance, but we don't need to talk about that much. One of the things that I have found, though, at Scripps is that I sort of decided to focus on ice shelves maybe 20 years ago. I mean, my PhD was on ice shelves, but a lot of people who look at Antarctica look at grounded ice, mainly like looking at the mass balance. The ice shelves are really where the rubber hits the road. They are, as I said, they're the buttressing agents. But at Scripps, the key thing is that the reason why ice shelves change is because they're interacting with the ocean underneath and the atmosphere above. And we have all of these pieces at Scripps. We have the geophysics, we have the ocean, and we have the atmosphere. And so it's been the perfect kind of by accident thing that I decided to focus on that's helped us, move so far in understanding ice shelves at Scripps. This is an event that happened very soon after I came here as a postdoc, after I finished my PhD. This was a real wake-up moment. I remember this. I was very, very shocked by this. There was another ice shelf collapse that had happened during my PhD, which I'm going to tell you more about right at the end, because you'll see a video of us landing here. But this was a Larsen Bay ice shelf collapse, which you may have heard about. It made every single newspaper outlet at the time. And what you see on this ice shelf is a lot of satellite image now, again, keeping an eye on what's going on, and you can see blue, lots of blue, right? Lots of bits of blue, and that blue is water, and the water is sitting on the ice. So you see these rifts here and crevasses. The water is inside those crevasses now, and water's heavy. If you've ever walked along with a bucket of water, you know how heavy water is, and ice shelves do not like water on top of them, especially not lots of water. It cannot support the weight, and so the whole thing just breaks, and that's what happened. Larsen Bay looked like this in January 2002, and by March 2002, this is what it looked like. The entire thing had just disintegrated, and little tiny pieces of Larsen Bay went into the Southern Ocean, ready to be tracked, just like I did when I was a student in Hobart, at MSSL. So you know, it's a cycle, but the cycle is actually happening really quickly in some places because the kick from the atmosphere causing the surface melt, hydrofracture, whole thing breaks apart. And so this was a real wake-up call. It was IPCC, AR, the first assessment report. I'm sorry, you were wrong. Like, ice shelves really do matter, and we've got to start paying attention to them. So this is kind of a very you know, what the glaciologists kind of have to really ramp up and start, like, you know, providing like predictions and things, and helping like get information into the IPCC to really like, well, what do we know about ice sheets? Let's get all of it in there and help with the modeling. And it was definitely a big time to sort of start working on ice shelves as a postdoc. I had a sort of I guess a slight career detour. And I think Nigella mentioned the subglacial lakes that I was involved in, but I just want to explain to you how I ended up in that position. I was actually mapping ice shelves, mapping the grounding line where the floating ice is separate from the grounded ice. You can do this with an instrument. At the time it was ICESat, but now we fly ICESat-2 NASA laser altimeter. And it is able to tell you the difference between where there's a tidal signal and where there isn't in repeat measurements of the laser, because ice shelves go up and down with the tides, but the grounded ice clearly doesn't, because it's not affected by the ocean tide. It's not floating on the ocean. And so I use this technique to map and monitor grounding lines at various places around Antarctica. But then I was looking at one place in Antarctica. So you see this grounding line here. This black line is the grounding line. So all of this ice under here, a very small chunk actually, is floating, but all of this ice is grounded. And right at the grounding line, it's funny, it's actually the first track I was looking at for this particular region. We found this signal, this here. And what it is just upstream of the grounding line, there was actually a subglacial lake that was draining. And so that's what this is. This is a 10-meter signal of the whole ice shelf grounded ice going down in steps. And over the 2.5 years that it did that, it completed a 10-meter drop. I mean, this is like, you don't see signals like this in Antarctica. Like, nowhere in Antarctica do you lose 10 meters of ice suddenly, but you do over subglacial lakes when they're draining, because the ice was sitting, the ice was sitting, resting on top, and I'll show you this little video that explains it. The ice is actually sitting on top of the lake, and the lake is at the bottom, underneath the ice, in between the ice and the rock. And when the water drains from the upstream lake on the left to the one on the right, the water's going downhill towards the ocean, but the ice is filling in to compensate, and the whole thing slumps down, which is what we measured with the altimeter. So the altimeter is actually able to detect these signals at the surface that are telling you about what's going on at the base, which is pretty cool. And so this was like a big stumbling thing. It was like, oh no, I want to look at ice shelves, but these lakes are actually super exciting too. So I kind of got distracted for about 10 years on that. I was actually in a position where I couldn't really do very much about this because I had loads of, like, my 2 kids were really little, and then we had a third one. All the field work that ensued from this was actually all my student. He went on all of the field work because I couldn't go, and ultimately sort of inherited a lot of the project. I don't know, like like a lot of the discoveries, and that's just, you know, the cycle of science, and it's great. We had a lot of success actually writing. Finally, well, the first proposals we wrote weren't successful, but we finally did get 2 projects funded to go and drill into some of those lakes. And there were 2 projects. So this is a map of all the lakes that we found around Antarctica. These are all the active lakes. And we got some funding to go and drill into 2 of them. And this one was a project called Wizard, which was Willen's Ice Stream Subglacial Axis Research Drilling. I did not come up with that acronym. And we were able to drill to the bottom of the lake and collect samples and things. This is about 900 meters of ice that we drilled through to get. But you see all the infrastructure, all the people that we needed for this. This is months and months of work, people in the tent. I mean, I wasn't part of any of this, but it was very exciting to witness it. And then another project that was called Salsa, and that one actually only just ended, and this drilled into another lake. And we've just had some papers coming out this week actually on some of the samples that came from that lake. We were able to gather from the sediments, like how old the lake is, some information about the deglaciation of the region, and going back to very interesting Holocene marine incursions and things. So yeah, very, very interesting work. But I kind of went back to ice shelves. I kind of like let all that happen and kept in touch with it and on the papers. But the ice shelves for me have always been the fascinating thing. And it's because what I said about what is controlling the mass loss from the ice sheet. They are the last thing that's holding everything back, and these buttresses and understanding how stable they are is really important for the whole ice sheet mass balance. Here on the left is it's a Spillhouse projection. Fred Spillhouse was a Scripps professor, and this is showing Antarctica in the middle of the oceans now, and showing you how important ocean circulation is, but how important the Southern Ocean is in particular for transporting, the heat and the salt and everything all around. So it's very much a very significant part of the meridional overturning circulation. And the Southern Ocean, loops around Antarctica. And what we noticed in looking at the changes in the ice shelves, so on the right here, where the red is on the ice shelves is where the ice shelves are changing the most. That's all you need to know. Where the yellow is, it's basically no signal. So these ice shelves, even though they're large, they're not actually changing very much. They're doing their job. The buttresses are safe. This is a good thing. We want them to be safe, because if they're not safe, this is when the ice starts to come off. So the wheels start to come off Antarctica when the ice shelves thin, and where that's happening is over here. So you see the red, that's where we're seeing most of the mass loss. You see a little bit over here as well, a little bit starting over here in East Antarctica. Personally, this is what I'm really concerned about, because this is most of our sea level potential. But this is a part that has caught the attention of most of my colleagues all around the world, Pine Island Glacier and Thwaites Glacier. So Thwaites has been subject of a very large field expedition, the International Thwaites Glacier Consortium, and they have done a lot of field work in here, trying to understand the processes and why this ice shelf is changing so much. And if you remember from the map from 1932, this is the area that we knew nothing about 90 years ago. And now we know that it's changing. We know why it's changing. We've thrown all this money at sending people in there and figuring out the interaction of the ocean with the ice sheet. You can see from the colors around the edges of the map here that this is ocean temperature, and you can see that the region where the ice shelves are changing the most is also the region where the water is warmer. So this water is sitting here ready to go underneath the ice shelves and melt them from below, and that's what's happening. So the place I showed you that disintegrated from the hydrofracture was up here. And that's mainly an atmospheric thing. So it's getting warmer in the northern part of Antarctica. But in this part of Antarctica, the main culprit for changing the status quo and putting the ice shelf out of balance is the ocean. So the heat that's in the ocean right now is extremely concerning. because that has the capacity to melt the ice. And that's what we don't want. So we were able to look at long time series of data. This is actually a 18-year time series to look at changes. What that can do is it can actually tell you something about the processes that are acting and what's actually driving the changes on the ice shelves. Student at Scripps, Fernando Paulo, did some amazing work on this and was able to extract a long time series, and we're able to see like which parts of Antarctica are changing the most as well and why. And then he also was able to isolate some of the signal that's happening in West Antarctica. He was able to pull out a signal related to El Nino. So on top of this long-term change, there's also a pattern that happens only during El Nino events, which is also having an effect as well, because these, and especially because El Nino events actually could get stronger as the climate changes. So this is really important for us to understand the what's actually driving these changes, this competition between the atmosphere and the ocean, and we need to know which one is having the most effect. So another student, Cecil Adesimili, has looked at basal melt rates. So how fast is the ice melting? And using the altimetry and now combining it with some other observations of how fast the ice is moving, you can actually work out basal melt rates, which is very important for modeling. We can now get freshwater fluxes from the ice shelves and put those into big climate models and figure out how this is actually impacting ocean circulation and other things. So this is all well and good, but how do you validate this stuff? I mean, you saw me on Amory in the 90s validating the altimetry, but how do you validate like the derived products from altimetry, like basal melting? This is kind of a difficult thing to get a handle on. Well, we did this project called Rosetta, which is a Ross ice shelf project where we flew over the ice shelf, but we also did this thing where we launched these instruments into the ocean. They're called Alamo floats, and we launched 6 of them all across the Ross ice front. They're able to dive and get ocean properties and things. So that helps us understand the actual ocean temperature and what's driving the changes on the ice shelves and helping to drive the basal melt rates. But this is an ice shelf the size of Texas or France, and we've only got 6 of these floats. So, it's really hard to actually get a proper understanding of what's going on with such sparse measurements compared to the size of the thing. There's also some other efforts, and this is British Antarctic Survey, who have these instruments called phase-sensitive radars, and these collect data on the ice shelves to get melt rates as well. But you've got to actually go in there, boots on the ground, fly a plane there, put someone on the ice and deploy the thing. And this is really hard on something the size of Antarctica. So being able to automate things and do it by satellite is definitely the way forward. So all of this is super important, and ultimately it comes down to this slide, because on the top left here, this is the sea level potential contained in the Antarctic ice sheet, and the darker the blue in these basins, these are the same basins that showed up on the early map I showed, the darker the blue, the more sea level potential. So 12 there means 12 meters of sea level potential. The scale is right here. So the lighter color blue are actually not such a large reservoir of ice, 1.3 meters in this basin, which drains into Thwaites. So Thwaites is a big deal because it's changing a lot, but it's actually not holding up that much ice behind it. The buttress is weakening, but the dam is not, the reservoir is not that full, right, in that reservoir. But the reservoirs that are very full are these ones. And these are the bridges or the buttresses that we do not want to be breaking. So we're very interested in our group in looking at the buttressing, like what's actually holding back all of this ice in these places where it's really, really a lot, and over here as well. I mean, luckily, we know that this ice shelf is pretty stable, but what happens if it goes out of balance? Then, so we need to keep an eye on all of these things. The big sort of thing about what's happening in the future with sea level rise is the largest uncertainty in future sea level rise is from the Antarctic ice sheet, because we don't know what's going to happen. And so right here, these are predictions going into the future for up to 2100. And there's this, you'll see there's this dashed line here. And this is it's a low likelihood, like the probability is low, but if it happened, the impact is huge because this is very large sea level that could kick in if some of these processes like fracturing, like rifting, like melting, we just don't understand them at the scales that we need to understand them to put them into our models. And that's the problem. We haven't had the observational capacity to do that. And so, you know, what's coming in the future, we actually don't know how much, how fast. We can't tell you. We have an idea, but the range is large. And unfortunately, that's the situation that we're in. But there is help coming and sort of looking forward to the future and living on a bit of hope is there are instruments that we are deploying that we've got flying that are able to make measurements at the resolution that's required to understand processes. This one here is ISAT-2. It's a NASA second generation NASA laser altimeter that followed from ISAT. And it is a multi-beam laser altimeter that's able to collect measurements at much higher resolution. You can see here what a great job it does of resolving things like rifts. So we're able to understand more the processes that lead to iceberg calving. It can also, it's a green laser, so it can see through water. So we can also get estimates of how much water there is on the surface. So that water that caused hydrofracture, we'll now know, we'll be able to monitor how much water there is on all of the ice shelves with techniques like this. We're also able to look from the old data to the new data and see how much the ice has changed over that time, which is about 15, 16 years or so. And we were able to do that for the entire ice sheet, including the ice shelves. So right here, this is the latest map, which came out a couple of years ago now. This is published in the New York Times from the article that we have published in Science. So this is their map. The New York Times made this map. Our map wasn't that great. I think that was the message. They did a much nicer one. And so where the red is where the ice is being lost. And this is all the same places that I showed you before. It's just getting more. Right now, other places are kicking in because we're able to resolve it. In here, we're seeing more red than we saw before. And that's because, you know, the processes are, things are kicking in. And we're seeing more and more mass loss in some of these places and some of these basins that are drawing down faster now because we're seeing melting in them as well. But it's not all it's not all mass loss. There is actually some ice being added and mass being added. As the atmosphere gets warmer, you actually get more accumulation, which offsets the melting. So that's good news. There is sort of a healing that can go on by the atmosphere, but these things work in opposition, and which one wins is very important for the whole sort of mass balance. So this is the latest map that we have, and it's from high resolution imagery called REMA. The satellites are worldview, very like 1 meter pixel resolution. So the improvement from what we had in 1932 is vast. We are able to also use the altimetry to make the imagery 3D. Right, you fuse the data. You have the satellite imagery and then the height data from the altimetry, and you can make a 3D map. It's kind of like virtual reality almost of the ice sheet, which is very, very nice and incredibly good for modeling and things like that. So this is what we have. It's called REMA, Reference Elevation Model of Antarctica. Looking to the future, the pathway for sort of improving sea level projections, the top left shows you the sort of arc of our understanding of how important ice sheets are, going from the first report that I told you about in the 90s, where, you know, the message was, did I just change what I'm showing? I seem to have lost what I'm showing. Okay, no, I was trying to use my cursor to point somewhere and I lost everything.
No, you're still showing the pathway to improved ice sheet.
Yeah, so here the arc of the first report, where we didn't really know much about climate change, and we certainly didn't think the ice sheets were important, and it's gone to much more understanding of climate change. The ice sheets are important. The most recent IPCC report, the assessment report number 6, which just came out, had its own dedicated ice sheet modeling into comparison exercise. That's what this is, ice sheet modeling into comparison project 6, dedicated for the AR6. I mean, amazing. We've come all this way over these 20 years. We now know how important ice sheets are to the point that we have dedicated modeling. So that's where we are as a community. We're running models to feed into the IPCC. We're also thinking about the next missions, which missions we need to launch to kind of, you know, make the observations that we need to understand the ice sheet and how it's changing, which is a lot of work with ESA and NASA. And this is the decadal survey, which I worked on, and yeah, like a huge document that just it basically goes through all the measurements you might ever want to make in earth science, and which instruments you might need to put them up and which ones are most important. So yeah, it's a lot of people, a lot of work, a lot of groups that I've had the pleasure of working with in my career. And this is some of the students and postdocs in my group and some of our collaborators. And yeah, it's really a wonderful time to be working on this, but there's also so much to do. But I want to leave it on a kind of very positive note. I know Nigella promised that I was going to show some slides from a recent trip I went on. So this was a very kind of last minute invitation that I got just before the holidays in December to suddenly be in Antarctica at the end of January on a luxury icebreaker to go to the Antarctic Peninsula. And I have to say, this is very funny. When I got the email, I actually thought it was a scam. I didn't believe that anybody would be wanting to suddenly take me to Antarctica, especially not on a luxury icebreaker. So I actually didn't reply. But my colleague Andy Shepherd was also invited, and he sent me a WhatsApp message about a week later and said, why haven't you responded? Like, are you not going to come on this amazing trip? And anyway, ended up going on this trip. So this is where we went. This is the Antarctic Peninsula that I just showed you. We were supposed to go down here. And it was quite funny because there's a piece of Antarctica named after me down here, which was a recent thing a couple of years ago. And they wanted to take the cruise there when they found that out. Like I told them about it when I saw the cruise route, and that was where we were supposed to go, which I was a little bit, I wasn't really sure whether I wanted that to happen. I thought that would be quite strange, the entire cruise going to something named after me. Turns out the weather worked in my favor. We didn't go there. We went on the other side of the peninsula. So we flew here and we went down this side. Now I've just showed you the Larsen Bay collapse here. So we then were on a mission to try and get down there because we wanted to take all the people on this ship. So I should actually say this ship is owned by Eric Schmidt, who is the former CEO of Google. He's now a major philanthropist and supporter of research for climate change. This was personally funded by him. It was not Schmidt Futures. It was not the Schmidt Foundation. It was Eric Schmidt himself. And it was called the Antarctic Science Expedition that he worked with a colleague of his at Sandbox AQ called Jack Hidary. And so this was all about like trying to get a group of scientists together to understand how AI and artificial intelligence and different instrumentation that they have on a ship like this, which is called the Legend, are able to contribute to Antarctic science and helping us to understand how to move the science forward quickly without being inhibited by the funding cycle that we're bound to and all this like crazy length of paperwork that we need to do for reporting and everything. They realize how important it is and how we shouldn't be belabored by that. So it was a wonderful opportunity. So here we are, like getting down there and going on our trip. This is where we went. We did not make it all the way to Larsen B. It was impossible in the time that we had, but we did make it to Larsen A. Now, Larsen A collapsed in 1995, which is when I was doing my PhD. So that was incredibly significant to me to be there suddenly in this place that actually was the site of an ice shelf collapse, but also there was new land that had been revealed after the ice is gone, and we could go on to that land. And I think I'm just going to jump through these and show you the video, which I was sent, because I think I just have enough time to show you that. This is me giving the talk I just gave you on the ship. This is Eric Schmidt here. This is one of the other people who was on the trip while we were approaching the Larsen A. I mean, it was extraordinary to me to be able to actually present the science in the place of the science. It was just like nothing else. I can't explain to you. So I'm going to leave, well, I'll flip through these photographs because you can see them, and I've got the thank you, but I want to show the video if I have time, Nigella. It's 3 minutes. Is it okay?
Yes, thank you very much. Let's see it.
I'm just trying to, I've got it loaded here. I need to. Do you see a drone looking down on a sea ice landscape?
Yes.
Okay, perfect. Right, I'm going to play it. Hopefully you can hear it because the music is very important too. So we had a photographer on board, a cinematographer, Richard Seide, and he made this. This is a drone footage that he used, and he put this whole thing together. So I'll leave you with this.
We're not getting the audio.
Ah. Okay. Thank you for telling me. How about now?
It's kind of garbled.
Yeah.
You can't really hear it.
You can hear it?
Not really. It's just garbled. No sound.
But it's still a very impressive video. Wow.
Well, we are right at what would have been the former grounding line of the Larsen Bay ice shelf in the Antarctic Peninsula. It's the northern part of the Larsen ice shelf. Disintegrated a couple of decades ago or more. And we just see so much here. We can see evidence of what's been left behind because of the glacier being here. So the landscape is really amazing, and we can see ice terminus that have been left behind as the ice shelf carved off and left. So the floating ice has gone away, and now we've got more or less a tidewater glacier. And we see refrozen meltwater, we see crevasses, we see all the signs of all the things that we know cause this ice shelf to disintegrate, which was essentially hydrofracture. It's amazing. For a glaciologist who's been working on Antarctica for as long as I have, this is like the most immense privilege. I can't tell you what it feels like to be here right now. Very honored. That's Eric Schmidt taking photographs.
We could hear your speech, so that was great. We just can't hear now.
Well, I'm really sorry that you couldn't hear it because it's actually really powerful. The music is very moving. So I will share the link with Nigella. Maybe she can distribute it. I couldn't speak.
Yes, I will.
It was so loud to me in here that I couldn't speak.
I can imagine, but you certainly, the video conveys some of the amazing excitement that must have felt going there.
Yeah, I mean, to actually like land on the beach with people that had never been to Antarctica before and just explain to them the enormity of like, I mean, and there was a running river and there was algae in the stream, and yeah, it was crazy. It was crazy. I mean, I can't explain how amazing that was. Like, just, I would say the highlight of my career so far. I mean, huge.
Wonderful, wonderful. I'm worried you're going to be late for faculty meeting.
Well,
So.
it turns out there isn't a faculty meeting today in the end, but I do have another meeting scheduled that I have to go to. So, but I would be willing to take questions like asynchronously, if you want to do that, maybe, or yeah.
Yes, I have a question to start with, and that is, you were talking about your concerns about East Antarctica, and because there's so much ice, ground ice that could go off. Are you organizing some grants and some expeditions there, you or your students, to understand that more? Because I noticed there wasn't a lot going on there study-wise.
I am involved in a little bit of that. I'm actually involved in a satellite mission proposal right now that's taking up all my time. But no, there are some people who are like asking for, logistics and funding to do fieldwork in East Antarctica. We're working with the Australian Antarctic Division, which is where I did my PhD. So right. Yeah, so yeah, there's definitely a lot of interest. It's ramping up. I mean, it should have been ramping up before. It's kind of too late, but yeah, there's I think people are realizing the importance of East Antarctica for sure.
You're good. Thank you.
Yeah.
Do you have time for any other questions? It wasn't clear. You meant about
yes.
One more quick question. I've just had to put the person off that I'm meeting.
Well, I'll ask one. Is that okay?
Yes.
I guess I might have missed it, but you had a slide where you were showing the ice being removed at the brown reddish areas. And then you also had like up in the north where there's more ice being added. And I didn't catch what you think that's due to. Why is there differential adding and subtracting?
Yeah, sorry, I kind of jumped over that. So as the atmosphere warms up in Antarctica, we're actually seeing more snow accumulation in some places because very cold air can't support, the moisture. Like snowfall doesn't occur if it's really cold, but as it gets a little bit warmer, then it's actually able to produce like more snow. So the accumulation increases. So there's like this funny thing going on where East Antarctica, actually that's happening. So some parts of Antarctica, the melting is being offset by the ice or the mass being added due to snowfall. So yeah, so it's kind of a competing thing, like the atmosphere is adding in some places, taking away in others because of melting, and then the ocean is melting. So all these things going on together are kind of like shaping the continent into what it's doing. On different time scales. It's very difficult because you could observe for 3 years and there's been a big El Nino event and something's happened, and then you get back again in 3 years' time and something else is happening. So you have to look for a long time to find trends.
I do see that Christine has her hand up. If you had
yeah, Christine, and then I will have to go.
Helen, right. Thank you so much in the first place. I would like to take you backwards. That is, can we, with your instruments and your research, say anything about the formation of Antarctica in the first place? And what comes to mind is Darwin. I mean, he crossed the Beagle Canal, and he must have seen that there was some life. And how did that play into his evolution theory?
Yeah, I mean, there is a lot of, basically collecting collecting samples from lakes and collecting samples from, you know, all around Antarctica. There's a lot of research and information being gathered by, you know, looking back at what Antarctica used to look like. Yeah, so you know, to be able to go there and set foot and take samples is the way, but obviously the satellite data don't really give you any of that. But you need to go there and collect the data.
Thank you so much, Helen, for a really fascinating talk.
You're
And
welcome.
we will put it up on our website, let you know, and I know we'll have a lot of members watching. So thank you so much.
Thank you. Thank you so much.
Thank you
Thank
very
you.
much.
Bye-bye.
Very interesting.